So, welcome everybody to this second day. We are happy to have you, all of you here, and we hope this becomes very fruitful and continues to go on over the following years. So feel free to interrupt the speaker at any time. He will be happy to answer and try to clarify whatever you think is not clear to you. So Damian is postdoc in King's College. He will be talking about the CENTAUR spacetime and holography. Welcome, Damian.
Hi everyone, can you hear me well, see me, see my screen?
Tutto bene.
I don't know, tutto bene? Okay, that's great. Well, let's see how it goes. Every now and then it says that my connection is unstable, so we'll see how that goes. Thanks for the invitation, and thanks to the organizers for setting up this nice meeting. So today I'm going to talk a little bit about the CENTAUR spacetime and attempts to describe it holographically. I apologize in advance for to all the experts in the audience. What I will be saying, it's quite basic, almost everything until the end, I hope. But feel free to interrupt and ask whatever you want. So let's go to it. My journey starts in 1998. And if we were there, I would look something like this. And actually, we wouldn't have Zoom, so it would look more or less like this. Our meeting, a bit more boring, but it was an exciting time because of two major developments that I guess you know about them, but let me just remind everyone. On one side, we have ADS-CFT correspondence, the first realization of the holographic principle, showing us how spacetimes with negative cosmological constant emerge from some kind of conformal field theory in the boundary, and I guess this HOLOGRAV group should know about it. But at the same time, there were some nice experiments going on, looking at the sky and looking at supernova explosions. And at the same time that ADS-CFT was born, we also realized that our universe is not described by a negative cosmological constant, not by a zero cosmological constant, but by a tiny positive cosmological constant. And this plot shows that these supernova are farther away than they should if we were to live in a universe in a flat with zero cosmological constant. So the idea of the talk is try to understand how universes with positive cosmological constant, like the ones we live in, can be described in some kind of framework closer to what we know about ADS-CFT. I got another unstable connection sign, so can you all hear me well?
Perfect.
Guille? Say something, because if not...
Okay, everything okay.
All right, great. So let's go to it. Who is the CENTAUR? The CENTAUR is this guy, Willem de Sitter, Dutch guy, talking to Einstein here. And together we have these nice equations that you all know. And today we will be interested in seeing solutions that have a positive cosmological constant. For now, I will stay in 4 dimensions, and this is the global metric of the CENTAUR. If you never see it, this is it. So tau is our global time coordinate. There is this L square here, some radius, say, and then we have a 3 sphere. So if we were to draw this space-time, it will look like this. So this is the cosh over here, and each constant, so tau will be growing like this, and each constant time slice will be a 3-sphere with a different radius that will grow. Well, it will start at tau equal to -infinity as an infinite large 3-sphere, and it will start shrinking. So these are constant tau slices. The zeta will start shrinking until it gets to tau equals 0. Then it will have its lower radius. Where we put the 0 here, we have L squared. And then it will start expanding. And this is the usual exponential thing that we know about zeta. So this is zeta. We can compactify this diagram to a PENROSE diagram. And this is our new de Sitter. Now it's a square, a bit boring. So this square, each is our 3-sphere, time is growing up. So we have tau equal to -infinity, that people call it scribe minus over here, scribe plus is over here. And each point in this diagram is a 2-sphere, except these horizontal lines that are just one point, the poles of the sphere. And okay, this is boring, so let's put some extra info to it. So let's concentrate on an observer living here on our North Pole, say. Here's the observer of my first slide. And okay, you see that this observer is sitting there, and everything that comes here from the past, flying these null rays, can affect this observer. So the region that can affect the observer is given by this green triangle. On the other side, we have the things that can be affected by our observer here, that can throw things into the sitter. And so the region that can be affected by our nice astronaut over there is this other green triangle. And this thing is the intersection of both and will be very important to us. If you are used to the diagram of the black hole, this looks pretty much like a horizon, and that's exactly what's going on. Because of this expansion, one observer in the sitter can only access a tiny portion of the full space-time. That tiny portion is this triangle over here, that it's called the static patch. And the metric for this static patch is given by this metric that I wrote over here. So it's pretty similar to the black hole metric, except that here the R coordinate starts at 0 at the boundary and then grows toward the horizon that is at R equals to 1. So this is kind of the difference between the black hole and the de Sitter horizon, and this simple minus sign will bring lots of problems. So let's compare a little bit these two things. So on one hand, we have this black hole metric in ADS. Now I'm putting all the L's to 1. So LADS is 1 and LDS is also 1. Here are the two metrics. As I was telling you, the F of R factor is just turn around. Instead of R squared minus 1, we have 1 minus R squared. So we know the black hole in ADS, we have an infinite boundary when R goes to plus infinity, and that's the boundary of ADS. And that's where we like to put our observers in of the dual boundary theory. The cosmological horizon is different because, as I was telling you, r equals 0 is just a point. The space-time is finite, all inside the static patch. There's no region where it grows infinitely large, as in the case of black holes. And then there's no natural place where to put observers, where gravity decouples, and we know what to talk about. Everywhere inside the static patch, gravity is relevant, and so what do we do? We also know, and this formula already appeared a few times in this conference, that black holes have entropy, have Bekenstein-Hawking entropy. Quite similarly, the CENTAUR horizons also have entropy, and this is something that Gibbons and Hawking wrote in a few years after the Bekenstein-Hawking formula. And okay, understanding this entropy is part of the puzzle in holography. We know that trying to understand what this formula is counting in the case of black holes eventually gave birth to the ABS-CFT correspondence, but we are still not there with the cosmological horizon. We might hope that if we have a holographic description of the CENTAUR, we might be able to understand what this Gibbons-Hawking entropy is counting. Okay, so that's my summary of holography. And so we go back to my first slide at the beginning. And this is what I was talking about. It's an observer sitting in the middle of the CENTAUR, surrounded by its event horizon, maybe trapped in Latin America, I don't know. But oppositely to what happens in the black hole case, there's no natural place where to put a boundary, where to have these nice observables that we like to talk about in ABS-CFT, and there's no place to fall, like in the case of the event horizon. So in the rest of the talk, I will try to show you a few things that we can do in order to try to understand these cosmological event horizons in a kind of holographic way. Of course, I'm not the first nor the last to talk about this. So the first, well, maybe the first idea came quite after the original ABS-CFT paper, and Strominger and Witten were thinking that maybe there's a CFT living not at infinite space, but at infinite time at scribe plus. That's the only place where the CENTAUR gets infinitely large. And then there were some more concrete attempts to it by these people. And let me remark here one of our members, Dio Aninos, that is in the audience. So if you want to talk about this DS-CFT, you can ask him maybe during the discussion or afterwards. I will be doing something different, but let me just give some other proposal that goes under the name of DS correspondence. And this is a bit more intricate. It takes the CENTAUR in the CENTAUR slices, and then the CENTAUR in D dimensions would be dual to some CFT in DS D-1. And I put this just to remark that here is another of our members, Gonzalo Torroba in Bariloche. So if you are interested in that approach to the CENTAUR, you can go and ask him. I won't talk about neither of these two. Instead, I will ask a slightly simpler question. And the idea would be, okay, we have this cosmological horizon that is finite, there's no boundary. What if we can cut a patch of this static patch and glue it to something that looks like ABS that will give a boundary to this cosmological horizon? Then we will be in a good position, because we will have our lovely boundary of ABS-CFT, and at the same time, inside the space-time, we will have a portion of the sitter that we might hope to probe with the usual experiments that we do in ABS-CFT. Okay, and this is also not new. All these people wrote a paper also many years ago, fostering this idea. And so the conclusion of this paper is that if you have Einstein's equations and you add the null energy condition, this is not the way they put it, but this is more or less what's going on. What you get are plots that look like this. So these are the type of PENROSE diagrams that they were getting. So here's the boundary, here's the boundary of ABS, and here's the patch of DS. But the problem with these diagrams is that every time they manage to glue the sitter to ABS, the part of the sitter is inside the horizon. So if you want to describe the sitter from this boundary, the problem would be at least as hard as describing the interior of the black hole. And that's a tough problem. So let me revise the null energy condition for you, because it will be important for us. So let's start in 4 dimensions. We put these ansatz for our metric. It will be described by 2 functions, f of r and g of r. G of r will give the size of the compact two-sphere, and this f of r will be the usual f of r factor. So what does the energy condition says? It says that if you have matter, your stress tensor contracted with any 2 null vectors should be greater or equal than 0. So if you combine that with the Einstein's equations, you will get some inequalities that both f and g should satisfy. And this is basically what you get. If we assume that f and g are both positive, then the first inequality is telling us that the second derivative of g is always negative, so it has some monotonic behavior. And then we have a more complicated equation relating g and f. Okay, so if we try to do our ABS to DS gluing, let me try to draw something that makes sense. Let's see if I manage. So I didn't. Okay. So if we start at the cosmological horizon with some radius, we said that the sitter starts shrinking, and eventually we will try to glue it to something like ABS. So it will have to grow and do something like this. So this especially this region over here will always violate this G prime prime less or equal than 0. And that's the problem they were facing. So instead, we will do something different, that is to concentrate in 2 dimensions, or in these solutions that are ABS2 crosses 2 or DS2 crosses 2. They are similar to what Joaquin was telling us in ABS or near ABS yesterday. So we will set the radius of the sphere constant to some constant R0. Then this equation is trivially satisfied. And we will glue ABS2 to DS2. This R0 is the same well, Joaquin was yesterday calling it phi naught, the large constant value of the dilaton. And we can also add a small r, a small running to this G of r, and that will also satisfy this null energy condition. Okay, so this satisfies the null energy condition. And so let's create these geometries. Let's consider a metric like this one. So now we have a constant sphere that I'm not writing anymore. And then we have this metric with this f of r. Sorry, my pointer is not working very well. But consider this metric that is 1 plus r absolute value of r plus dr squared over 1 plus r absolute value of r. Then for r less than 0, this metric will be 1 minus r squared. It will be our static patch metric. And for r greater than 0, this will be 1 plus r squared. It will be global ADS2. So this geometry is giving us what we want. Is a geometry that starts at the cosmological horizon. Well, we can start at the boundary. We go inside our space-time. Eventually, we reach r equals to 0, and that glues our space-time to ds, and eventually we will finish in our cosmological horizon. So these are the CENTAUR geometries that we were discussing with Dio and Diego Hoffman, another of the Siembra members of this team. And I think there was a question.
Damian, can I ask you
Yes.
one quick? So in this, in having the absolute value of r, when taking two derivatives and looking at the Einstein's equations, etc., somewhere the modulus will produce a singular behavior, right?
Yes, yes.
So go for it.
So you are right. R will jump from -2 to 2 in r equal to 0. But that won't be a problem. You can think about more smooth solutions. This is just like to show it here, this gluing, but you can think about functions that are asymptotically ds and asymptotically ADS, and they have some region inside that where you can glue it smoothly. And you can show when if you compute the thermodynamics or the action or whatever, you can show that all the effects coming from this small interpolating region will be subleading compared to this leading term.
So let me put it differently, and then if you want, push me to and then I let Gaston. So it will not be the presence of a source in this particular case with the modulus function.
No. This will be, I mean, it will be in 2 dimensions, so there will be no matter. It will be just the metric and the dilaton, like Joaquin was having yesterday, but the dilaton potential will be different.
Okay.
So there will be a dilaton potential that starts with a negative slope, and then when you go all the way into positive dilaton, it will go linearly and positive.
Okay.
So it will be a BJ potential, and in between you can have some smooth connection between the 2 regions, and that will give some subleading contributions to this metric.
Okay, thank you.
Gaston?
I have actually the same question as Carlos, but let me put it in a different way, because it's not your choice not to have matter. Matter is just something that happens when you just want to satisfy the boundary condition, the Israel boundary condition, or more generally, the continuation of the conjugated momentum to the metric. It's not your. So the question is, if you want to, at r equals 0, you want to satisfy the Israel boundary condition, or more precisely the analog of that. So you will have some source, actually. You will have some thin shell or something like that. Does it satisfy or not the energy condition?
No. So this is in 2 dimensions.
Yes.
In 2 dimensions, we will have a metric and a dilaton. And so the action will be something like the dilaton gravity action with a potential for the dilaton field.
Like a Shakib-Teitelbaum thing, right?
Like Shakib-Teitelbaum, but in Shakib-Teitelbaum, we have u of phi equal to plus 2 phi. This thing will be something that starts at -2 phi, will reach r equals 0, and then will grow like 2 phi, like JT. And that's everything you will have. There will be no extra matter.
Okay, but I mean, you can see still there are some boundary conditions to be satisfied. Even in that theory, there is some boundary sanction condition.
There will. No, there are no sanction conditions. You put a potential in 2 dimensions. There's a potential. You get a metric for that potential.
Okay, so suppose let me put in analogous terms. 4-dimensional Einstein gravity, no matter, nothing, just Einstein gravity. You do have sanction condition there, the Israel sanction condition.
Yes.
Here is the same, right, or not? And why it's not? It's not because only have the metric and the dilaton, because in Einstein gravity, you only have the metric and you do have sanction condition.
So if you want to uplift this into higher dimensions.
No, I don't.
I was telling you.
I don't.
Okay, then you don't have Einstein. You don't have any.
In this theory, so you mean that in this theory you don't have sanction condition to obey, just they're automatically obeyed. That's the point.
In this theory, the only thing you have is the potential for your dilaton, and that dilaton potential specifies your metric, and that's it. That's all that you have. You have the dilaton potential. Well, then I can show you the equations, but that dilaton potential specifies your metric, and that's it. That's all.
Let me put it in other terms. If you compute your metric for your 2-dimensional metric, your extrinsic curvature, does it jump or not everywhere 0?
The Ricci scalar in this metric will
the extrinsic curvature. No,
the extrinsic curvature. Well, I don't know. I will have to think about it.
Maybe Gaston, we can leave it for the discussion, not to take too much time from him. Is it okay?
I will never finish it. Not.
Until
what time do I have?
I think that you still have half an hour, so take it.
Okay. Okay. All right. So this is our geometry. If we look at the PENROSE diagram, it will look something like this. So now this will be ADS. This will be our interpolating region, and this will this will go into DS, and we will have a horizon here. Oops. And now so now we have a geometry that has the ADS boundary. It has a different behavior in the IR, and we can start playing with it as we do in ADS CFT. In holography, we can start putting different probes to try to understand the CENTAUR horizon. So that's what we did with Dio and Diego in a paper at the end of 2018. And as opposed to the diagrams that I was showing in the previous slides, now the CENTAUR horizon is in causal contact with the boundary. So we can, we can access the event horizon from the boundary of ADS. Okay, and with this, now we can start doing different experiments and trying to characterize the CENTAUR horizon and see how this is different from the usual black hole horizon. So, well, the discussion already came in before, but I wanted to say a few words about 2 dimensions. So we don't live in 2 dimensions. This is a picture from Hawking's Brief History of Time. I like it. So let me say a few things on why we think it's interesting to see the problem in 2 dimensions. The first thing is that these 2 horizons share many features with the higher dimensional versions. Basically, the finiteness of the static patch is still there in 2 dimensions, and that's what we would like to understand holographically. Finiteness of the CENTAUR might be related to having, well, a finite Hilbert space in the dual theory. So maybe talking about quantum mechanical models in the boundary might be a nice way to go. And also, as Joaquin was telling us yesterday, there are lots of recent developments regarding JT gravity and SYK models in the boundary and matrix integrals and all this. So maybe all this technology can give us a new insight into the problem of the CENTAUR as well. And my last comment about 2 dimensions is that the CENTAUR in 2D also appears as a solution of the Einstein's equations with positive cosmological constant in higher dimensions. This is called the Nari solution, and it's equivalent to the near horizon limit of extremal black holes. So we can have a black hole in the CENTAUR. It will be given by this metric now. The f of r will be this 1 minus r squared that we had before. Sorry, but now we will have this black hole factor. So this is the PENROSE diagram of the CENTAUR black hole. Well, we can go to this square one, and then our r coordinate will be trapped between the cosmological horizon and the black hole horizon. It will have 2 horizons for small r. They will be given by this, but that's not important. The thing is that when we start increasing r, there will be some point where the 2 horizons will collide, one to each other at this particular value. And then the idea of this limit is to get slightly out of it. So consider the cosmological horizon being r plus epsilon and the black hole 1 minus epsilon. And then we can consider our coordinate close to the horizon, and we can expand our metric. And we will see that in this limit, when we take epsilon to 0, we get that the metric is given by ds2 cross s2. So sorry, ds2 cross s2. So even in higher dimensions, ds appears without needing to add any angular momentum or rotation as we usually do in the extremal black hole case. So let me finish here my disclaimer. I don't want to be less than Tomás. So my last point of this disclaimer will be that this will be some kind of realization of Borges' the Aleph, where there is this one point. The boundary will be this point that has this quantum mechanical theory, where all other places of our universe will be seen from every angle, each standing clear without any confusion or blending. So, end of my disclaimer.
No. Sorry,
yes.
There's a comment of Alfredo. I don't know if Alfredo wants to unmute and make a comment about Gaston. Okay. Maybe I think, okay, maybe just to say.
Yeah, we can discuss it later during the discussion.
Yes, we will lead to the discussion. Go on, Damian.
All right. Okay, so now we have this geometry in 2 dimensions. We can develop all our holographic knowledge. I put all that in this green square because I don't want to go through it in a lot of detail because I don't have time. But sorry, this is the next part. So, well, okay, given that people were asking, let me just say it briefly. So we will start with a 2-dimensional dilaton gravity theory where we have the metric and the dilaton. There will be this B of phi, that is the dilaton potential. And when B of phi is equal to plus 2 phi, this is the JT theory that Joaquin was describing later. The equations of motion for this action can be given for any potential. So R will be equal to minus B prime of phi, and there will be an equation for the dilaton that I summarize in T mu nu equal to 0. And then we need a dilaton potential that does the job of interpolating between ds and ds. So we will need something that has linear negative slope asymptotically when phi goes to -infinity, and will be +2 when this goes to +infinity. And the final point will be boundary conditions close to the ADS boundary. So we will put some value phi b for the dilaton and some value h mu for the induced metric at the boundary. And these are the same boundary conditions that Joaquin was telling us yesterday. So once we have this, we can do what we always do with holography. We can find solutions, we can put them on shell, we can compute the thermodynamics, we can add matter, compute different types of correlators, and all the things that we like to do in holography. We did many of these holographic experiments. But okay, today I want to tell you briefly about a simple one. We did compute out-of-time order correlators, 2-point functions. We computed the effective Schwarzian theory. We did many things, quasi-normal modes, but okay. Let me just concentrate on the shockwave experiment because it's simple and I can draw it here, and I guess people more or less know what happens in the ADS case. So let me review that first. So Dre and Toft were the first to study this, and the thing was revived by Schenker and Stanford, well, now quite a few years ago. But so the idea is to start with the eternal black hole in ADS. Now I move to these UV coordinates. Here's the metric. This is the eternal black hole. This is the PENROSE diagram. We have two boundaries that share the interior of the black hole, but do not talk to each other. So if we throw anything from the left boundary, it will never reach the right boundary, and the same. What you can do is to send something from the right and send something from the left, and they can meet inside the event horizons. This is called non-traversable wormhole. And the idea is to see what happens when we add a shockwave to this solution. So we add some perturbation at some time close to -infinity, +infinity, depending on how you call the times. So basically, you add a stress tensor that is a delta function in U with some coefficient here alpha, and you solve the Einstein's equations. And everywhere outside U equals 0, the solution is just the ADS black hole. So now you need to glue the two regions accordingly. And the solution is quite known by now and looks like this. So this is the new solution. This is the new PENROSE diagram, and this is the way we are gluing the two horizons. There's a shift that is given by this constant alpha between the two horizons. And if before it was non-traversable, the wormhole, now the situation is even worse. Things, well, yeah, there's this positive shift between the horizons that makes things even worse. This is the metric. It can be seen as there are different ways of putting the metric. You can write it like this, or you can write discontinuous coordinates, where then you will have the metric with a delta function that is the usual shockwave metric. Okay, now we can do the same experiment with our CENTAUR geometry. So we want to see what happens in the CETER. In the CETER, if we do this experiment, well, okay. There are shockwave solutions in the CETER, and there are theorems by Gao and Wald that says say that the diagram, the PENROSE diagram in the CENTAUR always become taller when you put this extra matter. But now with the CENTAUR, we can analyze it in a, say, more modern holographic way. We can interpret this shockwave in terms of the boundary. And what happens is that we start with our double-sided CENTAUR geometry. We make the perturbation, and one of the solutions that we get looks like this. So now alpha goes kind of in the other way, like to minus alpha, and now what before were unconnected boundaries now become connected. So the diagram grows taller, the two horizons shift between each other by an amount that is of order alpha, and now you get the two boundaries in causal contact. And this, again, in ADS, you can always do it. You can only do it with a negative alpha. That would mean having a negative stress tensor. All right, so it was a short experiment just to show the differences between the usual black hole horizon and our CENTAUR, the CETAUR horizons. So as I was saying before, in ADS, if you want to connect the two boundaries, you can only do it a la Gauss-Jeffreys wall, adding some negative energy in the bulk. In the CETAUR, or at least in these CENTAUR geometries, you can connect the two boundaries while satisfying the usual energy conditions. This looks very simple from the macroscopic, from the space-time diagram, but it's kind of hard to understand from a microscopic perspective. What is the dual quantum mechanical theory doing that it makes the shockwave solution in these geometries to behave in this way? So this is one of the puzzles we would like to solve, but now we can put, sorry about this, it's not my iPad and it keeps putting notifications. But now, yeah, we can do these experiments, and now we can translate into the boundary, and we can ask what type of boundary theories behave in this way. So let me summarize a little bit. So we constructed these geometries that interpolate between ADS and DS in 2 dimensions. Once we have these constructions, we can use the usual ADS CFT correspondence to characterize these macroscopic geometries, and we have quite a lot of evidence to say that cosmological event horizons viewed from this holographic perspective behave different to black hole horizons, even though they do have a temperature and an entropy like Gibbons-Hawking were telling us. So we have many questions about this and how what are the microscopic realizations of these type of flows from ADS to DS, and we started analyzing these things with Dionysios in a paper that came out a month or 2 ago, where we tried to first strengthen a little bit the holographic dictionary in 2 dimensions in order to be able to translate these macroscopic features into microscopic observables, and we then analyze different types of RG flows that are solvable in SYK models, where the dual geometry should be doing something like this interpolation between 2 different regions. Of course, eventually we would like to get rid of the ADS part and have a theory just for the sitter, and people were studying this idea in the context of TT bar deformations, if you heard about this. There are many other experiments I didn't tell you, but we did. There's a very interesting thing happening with the out-of-time order correlator related to quantum chaos that in these CENTAUR geometries oscillates instead of growing exponentially as in the case of black holes. And one can think of many different experiments that one can do, and that would be another thing that the de Sitter microscopic theory should satisfy. CENTAUR geometries in higher dimensions, I guess this is related to what Gaston was asking, or maybe not. What is the relation between this approach and all the other de Sitter approaches, some of which I told briefly at the beginning of the talk. And more general, in this two-dimensional gravity theories, what other features we can have in the bulk of ADS2 is an interesting question to think about it. We particularly are interested in de Sitter, but you can think about other things inside, especially because of this freedom that somehow you have with this dilaton potential. All right, so this is basically a summary of this idea of gluing DS into ADS in 2 dimensions, and we hope that eventually, well, there are many questions to explore, and we hope that eventually this will give us some insight into the real questions about the Sitter holography. What is the dual quantum field theory? Is it unitary? Is it conformal? What's the Hilbert space? It is finite. What's the Sitter entropy counting? What about observer dependence? And the many other questions that arise when talking about holography in the Sitter. So I think how am I doing with time?
I think it's okay, because now we can go to the question. So
okay, so let me finish here. I have just one. Yeah. Well, these are my collaborators, Dionisios Aninos and Diego Hoffman. I started looking at the people working in the Sitter in the Siembra community, and I saw there were a lot of them. So I won't mention them, but it's nice that we have so many people here thinking about this problem, and I hope I might convince some of the younger ones that this is an interesting, hard problem to think about. Joaquin, well, Tomás cited Borges. Joaquin gave a lot of exercises, so I want to finish with an exercise that I took from the Lesouche lectures by Strominger, that of course you all read and analyzed for this talk. It was in the suggested bibliography, and they end up the lectures by giving one last exercise that basically says, sit down and find the dual of the Sitter. Thank you. Okay. That's all that I have to say.
Nice talk. Nice.